Everybody got all the food they want. Okay, so I'm going to be talking today about general relativity and Schwarzschild black holes. We're going to start by talking about Newtonian physics and why it doesn't work, and then we're going to go on to Einstein and how he corrected the small errors there are in Newtonian physics, what his theory means, and stuff like that. Then we're going to go on to what I consider the most interesting class of objects found in general relativity, which are black holes. So there's a brief history of pre-Newtonian thought on gravity. As far as we're concerned, there wasn't much of it. Aristotle had some good ideas, but we're not going to talk about him today. So it really started with Newton. Newton's laws, the key points of them are encapsulated here. You got the theory of universal gravitation, the second law of motion. And you can see when you substitute these F's, you get a simple result that the mass, little m, drops out. This is why all falling bodies accelerate the same, regardless of the mass, right? So there's a modern theory, and Einstein came along and corrected this. And we're going to explain, this is Einstein's field equation, or his field equations, and we're going to explain what they mean, why they're plural later. But for now, note, this was published on November 11th, 1915. That makes this the centennial of Einstein's theory of general relativity in 5 days. So this talk, it could not have been planned better. It turns out that I get the last slot before the centennial, so you guys can all know about it and learn how to better celebrate the centennial, which is just a momentous event. Okay, so we're going to talk briefly about Newtonian gravity. So a classical problem is the three-body problem, right? And you've got three bodies, it's unrestricted, which means they can all move about freely as affected by acceleration due to the other bodies. So you think this one will move a little bit due to the mass of the others, and this one will move a little bit due to the mass of the others, but it's dependent on the position, which is in turn dependent on the acceleration, and you go on around and around infinitely, recursively in this loop. And this is called iteration. So this is the Euler method for iteration, if you're not familiar with it. It's the simplest one. There are better ones, but we're not going to talk about it because we only care about the concept of it. So you got some initial state, and you set it up with an initial velocity and initial position. So we're going to add an acceleration, which we calculate from the position of the environment. We're doing this simply in one dimension, right? But you understand it can be generalized to as many dimensions as you want. And we're just assuming you can calculate your acceleration based on the state, right? It's not interesting. But you multiply it by a time delta, and you can make this small and get it to an arbitrary precision, however you like. And now this gives you your new velocity, and you add this to your time, do the same, or your position, and do the same thing with the time delta. So this looks like these equations if your acceleration is constant and your time delta is small enough. Now, we're interested today in talking.
Acceleration doesn't have to be constant. That's the point of it.
Yeah, that's true. Thank you. Well, but it's difficult to calculate if your acceleration is not constant, because if your acceleration is dependent on the position, you see, this is why you can do some of these problems analytically. There are some stable states of the three-body system which you can calculate analytically, but generally you need to do it numerically, right? So what if we want to do with photons? Here we've got where c is the speed of light, initial velocity is c, and initial position x we don't care about. First thing we're going to do is add the acceleration times the time delta, but we immediately see, since acceleration can be positive, we're adding something to the speed of light, and we get particles traveling faster than light. So this is something I naively tried to do at the beginning of the semester, and I had particles traveling faster than light everywhere in my simulation, and it was horrible. So if you want to do this, you need to be aware that this doesn't really work like this. You can't accelerate light. It doesn't make sense. So compare this to the central problem with special relativity. And so many of you I've either had modern physics or will be taking it next semester. It's offered. Yeah. So one of the central problems we talk about is that we assume speed of light is invariant in all reference frames. So this means, like, here's a classical analogy. You're moving on a moving reference frame like a train with some velocity, call it v, and you throw a ball with velocity u. Then relative to a stationary observer, you expect the velocity of the ball to be v plus u. But what if the ball is actually light? It's traveling at c. Do you expect the velocity relative to a stationary observer to be c plus v? No, it can't be greater than the speed of light. So you get this result, and this is something you calculate in modern physics, and it's not hard. You get it from first principles. But all this says is that the real velocity, for small velocities, it looks like you're adding them. But really, you can see the limiting case of this is where both of them are c. So you have 2c in the top, 1 plus, that turns into 1, so you get just c is the maximum velocity under this velocity addition. So Now, there's a limitation of this. This is only dealing with inertial frames where there's no acceleration. But our original problem, we wanted to simulate photons under gravity. So we need something more general than this. I hope you see where this is going. But first, we're going to talk about acceleration. So there's this principle of equivalence of acceleration between acceleration due to gravity and acceleration due to, well, just acceleration. So, for instance, if I put you in Heiser and blacked out all the windows, could you do any experiment to determine whether you're on Earth experiencing Earth gravity, or if you're actually in space uniformly accelerating upward at 9.8 meters per second? It turns out that there's no experiment you could do, barring tidal effects, but that's not relevant. So Einstein saw this, and he said that light should be bent by gravity. And it's not obvious how he got to this, but let me quickly draw a diagram. I can never find a good graphic of this, so I'll do it on the whiteboard if you don't mind. Imagine you've got some reference frame, and you're going to accelerate this frame upward like this. And you can see that this is like time equals 0, time equals 1, time equals 2. Okay? So it's accelerating upward in a parabola as time goes on. Now imagine if at time equals 0, you send out a photon from here. Okay? And the photon goes in a straight line relative to where it started, right? So it's going to go like this through the reference frames. And if you were to draw this, if you were to project this into this reference frame, it would look like a parabola, because it's the same way that this is going upward in a parabola. Relative to the inside of the frame, it looks like this is falling. So Einstein said there's no reason that under Newtonian gravity, we shouldn't expect light not to accelerate just because it's massless. He said acceleration doesn't have to do with the mass of the particle. It's something different than that, and it has to do with space. And we're going to talk about that in a little bit. And it's kind of, I'm jumping ahead showing this. But the point is that there is this thing you expect, which is that light will be bent by gravity. And we'll talk about the formalization of that. But for now, it's like this. So here's light from a star, and this projects back to where we expect we'd see the star, or where it would appear like the star is coming from. So here's the 1918 eclipse. 3 years after Einstein published his theory, this occurred, and it was very lucky because we were able to measure it. And these two tick marks up here, the top one is where we observed the star. And the one right below it is where the astronomers told us we should have observed the star, and it's off by about an arc second. And this turns out that it's exactly what Einstein predicted we would have seen if the light's being lensed or bent by gravity, as on the previous slide.
So is this diagram to scale?
This is a picture.
Yeah, I mean, yeah, it's the sun, but your arc second shifting, is that to scale, Alex?
Is it to scale relative to
of your sun?
I believe so. Well, no, it does seem like it would be. Perhaps this is exaggerated. You might be right about that. It does seem like it's too big. This looks enormous. That what you meant? Yeah, you're right. The actual bending was about an arc second. I think 1.7 arc seconds.
And how big is the sun?
It's got to be. That's my distance question. Like half a degree, or on the order of half a degree. Madison, what is it? Okay. I'm not an astronomer. I don't care. Sorry. This is more interesting. We'll talk about this instead. Yeah, fair enough. Okay, so we're going to talk. What was that? Yeah, thank you.
You're not that short of time, so don't worry if questions come up.
Okay.
Don't feel you've got to rush.
Yeah, I know I'm rushing through this a little bit, but I think you'd rather I do this than have you here all day, right? So here's a picture of flat space, and this is like a triangular lattice. And you imagine these are all equilateral triangles, and I'm telling you that they're in flat space. It's possible for them to be different. But the point is that distance across here is the same in every direction, right? And you can imagine that if you were to take the legs of these lines around a point and double their length, it would sort of jut out from the space, like that. And what you would have there is an instance where the distance between 2 points, like on either side of it, would be different. So this is in Euclidean space. This is like R2, right? So we have something called Minkowski space, and Minkowski space is what we do all modern physics in. And we're going to talk specifically about what that means in a second. But for now, just think of it, it's Euclidean space with time. So these are Einstein's field equations. And fast counters in the audience will immediately remark, that's not a set of equations, it's one equation. But in reality, it's 16 equations, because there are indices. These things, it's a tensor equation. And what it says is it states a physical relationship between the curvature of space, which is on this side, and the mass energy distribution in space, which is on that side. And it says this is true for all of space. So specifically, this is the Ricci curvature tensor and the Ricci curvature scalar. These talk about how the space is curving at a given point. This is just how much it's curving. This is specifically how it's curving. The metric tensor is very important, and I haven't defined that yet, but we'll talk about it in just a minute. Lambda is the cosmological constant. That's like the expansion of the universe, and we're definitely not going to talk about that now. And so we've got that again. So this is all to do with curvature. This could be represented in your metric tensor. This is derived from the metric tensor, and so is this. This is derived from that. And now you say that this is all equal to some fundamental constants. Those are nice because you know you're doing physics. And times the stress energy momentum tensor. So I should note that in Einstein stuff, mass and energy, momentum, these things are all very much synonymous. So for the remainder of the talk, I'm probably just going to say mass, but understand that I could also mean energy or momentum, which is just energy, which is just mass. Which is just, no, kidding. Yes?
You said mass energy distribution. Is that like a density kind of thing, or like?
Yeah.
Okay.
Yeah, it would be like a density. So so it's a field equation, right? So you're familiar with working with like a scalar field or a vector field. Here you have a tensor field. So you've got like, at every point in space, some mass distribution, so you're saying mass energy. And that is going to be equal to the local curvature or whatever's on this side. And it's different depending on how you set it up. So here you've got some exact solutions to Einstein's field equation. First, the vacuum solution is kind of enlightening. Let me go back to this for just a second. This says if you are in a vacuum universe and you have no mass or energy anywhere, that this side is zero. So you'd expect this side to evaluate to zero. And a way that that could happen would be you've got this, no curvature anywhere, that's zero. Your Ricci curvature scalar everywhere is zero. And then your cosmological constant is zero. So you see how that satisfies the equation. That's this trivial case. So the first non-trivial case is the Schwarzschild metric, and that's what we're going to be talking about today. These three below it, we're going to get to right at the end. They're also, these first five have physical analogs. Other ones are a little bit more convoluted, how they would have physical analogs. Like this Van Stockham dust, it's like some strange case, I believe, where you have like a cylindrically symmetrical mass distribution of dust filling the entire universe, rotating around an axis. And it's like, that's evidently satisfies this, I don't know why. But these have nice analogies, okay? So I've been talking about
the guys that used to do solutions like that are now doing, now including quantum mechanics and string theory, and you wouldn't believe what they come up with.
Yeah. So this is
as in, you don't want to see it.
Yeah, there's some strange ones. This is by no means an exhaustive list. There are a lot of things you can say about this. In a lot of ways you can, what do you call them, extensions or something, where you add these other theories and you try to make them work together. Like you want to make quantum gravity work, and you want to make quantum physics work with this. And it's like you take two very complicated things and put them together and see what you get. It's a mess.
But no quantum mechanics here because there's no Planck's constant anywhere in
no Planck's constant in any of these. I would be really scared if I saw Planck's constant. No. Okay. So these all say metric, right? But I haven't defined what a metric is. So a metric, first of all, they're great. That's the first thing to know about them. They describe what distances and angles look like in your space. Okay? So for an n-dimensional space, they will look like a symmetric n by n matrix. All right? And they're in this form, we note them G, but they're in this matrix form so that they can work like an inner product is the spoiler. And they take two linear functionals like vectors, and they will map them to a scalar, like your inner product does. And inner product, scalar product, dot product, these things are all synonymous to my knowledge. So I might say one or the other. Understand that I mean whatever one you're most comfortable with. So here's some instances of spaces where it's not really clear what your distances and angles look like. This is like positive curvature and negative curvature. You got the Pringle. Yeah, so it can be complicated. So we're going to look at some simple ones. The simplest one, of course, is just for Euclidean space. It's just the identity matrix. And this makes sense because you say you want it to act like your inner product. Well, what if you multiply on one side, you got like a row vector and a column vector on the right side? They would act like an inner product if you did matrix multiplication on those things. So this is nice. It's just an inner product. It's positive definite. Oh, I wrote this here. That your distance function, it's just the inner product. You know, that's how you find the magnitude of something. And it just looks like the Pythagorean theorem. That's what we're used to seeing. This is distance. So for Minkowski space, it's a little bit different. We call this eta. And it's not positive definite. But I should say that about the first one. The first Euclidean space is positive definite. That means if you take any 2 points in your space, the distance between them is definitely positive. Or it could be 0 if you pick the same one, if the same point. But this is not positive definite, because you can see that if you pick some great distance separating your points, I should say this is time x, y, z, something like that. This is time, though, and these are 3 dimensions. So if you pick some points that are very far apart, but at a time delta that's small, then the metric, this will evaluate to a negative quantity. But this means, it turns out it always is negative if what you've chosen are points that are too far for light to traverse between them. And I mean points in space and time, so events really. So it turns out it's always positive if what you've chosen makes sense, basically. And we could talk all day about this, but I don't want to. And I've surreptitiously added a C in here because in GR they like to set C equal to 1, which is nice. It's called natural units. It's very confusing. But it's okay to add that because I'm just multiplying it by 1 squared. So, yeah, and it's not positive definite. Okay, so now we're going to quickly go through a simple example. I think, hopefully you're all familiar with spherical coordinates. So we've got here a change of coordinates, right? And we're going to do it for the unit sphere. We're going to try to derive the metric. So the unit sphere is just where r is equal to 1, okay? So I got the change of coordinates. I put it in a vector form up here, all right? I'm going to call that psi. And now I'm going to take the derivative, and this sub theta and sub phi denote the derivative with respect to theta and phi. So I differentiate it. It's just a bit of calculus. And then you take the inner product of each one. That's that inner product, and I hope you can read that. But the inner product of this with itself, and then this with that, and then that with this. It turns out it's symmetric, and this is what gives you your metric tensor for any space where you have the change of coordinates. So, all right. Now, we're physicists, right? So we want to know what it looks like when things move in space. Yeah? So what are our trajectories look like? It turns out that they look like the shortest path. What path do things actually take? It says the shortest. And this is due kind of to the principle of least action. I don't fully understand, though, how that works, so don't ask me a question about that. But basically, I think I've got a nice picture. Oh, these are called geodesics, these things, because you imagine, like, what is the shortest path in your flat space? What is the shortest path between 2 points? It's clearly a straight line, right? But what if your space is curved? It's not obvious what it's going to be. So we call it a geodesic. And here's a picture of some geodesics. These are actually flight paths around the world. And I hope you can see it. It's kind of dim on here. But, you know, here's like the US and Europe. Yeah? So it turns out that the airlines know about this, and they go the shortest distance between any 2 points on our sphere. And this is the most efficient thing to do. And nature does the exact same thing. It takes the shortest distance between 2 points. So they're both geodesics. But how do we calculate the geodesics? I'm not going to go through this, but schematically, you take your metric tensor, and it gives you something called Christoffel symbols. And these are kind of tedious to calculate, but, well, I'm not going to really talk about them much. But that's what they're called, and they give you geodesics. And I'll show the equation for them in a moment. This, incidentally, also gives you your Ricci curvature tensor and your Ricci curvature scalar. They come out of the Christoffel symbols. So this is where you get them. It's from this this equation here, and you can see where your matrix is orthogonal. Then it reduces to this. And it's like becomes obvious if you try to calculate them. So this is given by the people who do differential geometry, and I don't understand where it comes from. It's very complicated, and this is the extent of my understanding. I know that we are given this equation. It's a lot harder to figure out and to understand where it comes from. It has to do with connections. That's all I know. Yeah. The geodesic equation. This one's a little bit more intuitive. Well, I won't say that. It's also given. We'll just accept it, take it for granted. So these are the things where you can calculate your geodesics based on the Christoffel symbols, which take your metric, give you the Christoffel symbol, and then the geodesic equation, which relates the second derivative of whatever xk, it could be x, y, z, or t, not in that order, plus the sum of the Christoffel symbols. Okay, so this all seems kind of meaningless, but let's do an example. So we calculated the unit sphere before, and we'll take that, and I already computed the Christoffel symbols. 5 of them are 0, and it turns out if you plug them into the previous equations, you get these. And you remember what, you might not be familiar with what cotangent looks like. It's 0 at pi over 2. So let's set theta equal to pi over 2. This becomes 0. This all goes to 0, because your second derivative of theta is a constant, is 0. So this is satisfied, and it turns out it's satisfied for the equatorial plane, the equatorial great circle. So we said before what great circles are, right? They're the biggest circles you can make on a sphere. All right. So it's a great circle. That's your geodesic. The shortest path is going to be along a great circle. And I've got a sphere here, it's like the equator. And because you've got SO3 rotations in the sphere, you can say that you're done, and that can give you any great circle. Like this. And the airlines know about this. Okay, so now we've been talking only about math. Let's talk about black holes. They're very, very interesting. We'll start with the question, what keeps a star from collapsing under gravity? The first obvious answer is, well, it's the pressure of the hot material in the center of the star. It's bouncing, atoms are bouncing all against one another, creating a pressure, and it's at an equilibrium. Okay, that's good. But what about if we have a lot of gravity? So much gravity that this cannot resist the force of gravity. It turns out the next thing that will stop us is, it will stop at a place called the Chandrasekhar limit. This is where the thing resisting gravity is electron degeneracy pressure. This is where electrons refuse to occupy the same state. And this is due to the Pauli exclusion principle, which says that electrons, they can't occupy the same state. I thought I put something very well. What about when it's stronger than that, though? What if we overcome that? Because that's going to have some finite strength that we can resist, right? Well, it turns out if it gets stronger than that, it can overcome electron degeneracy pressure and collapse further, pressing the electrons into the protons and kind of turning them into neutrons. And you get this, that process is a little bit fuzzy to me. It's photodisintegration is the general name of it, but I don't study particle physics, so I don't understand it. Someone asked me about it. So now you've got a neutron star, and it's being held up by neutron degeneracy pressure. This is the same thing where the neutrons refuse to occupy the same state. So I think you should all be familiar with degeneracy. We just talked about it in thermal physics. So it's, you just can't have, if you have a degenerate electron, that would be like the same state has 2 electrons in it, right? So this would be the same thing with neutrons, where neutrons would be in the same place. So this is very powerful, but what about if gravity is even stronger than that? And it's not unreasonable to think about that, because you might think you've got very powerful phenomena in astronomy and astrophysics, like a supernova, and it gives you this incredible force. So this, it turns out, can overcome neutron degeneracy pressure. And the question is, what can hold you up if neutron degeneracy pressure can't? And the answer is nothing can. The star will continue to collapse in on itself until it reaches a point where whatever angular momentum it once had has been accelerated like a ballerina, and it's now rotating at the speed of light. That's the last thing that holds it up. So you think that it will collapse down to a very, very small point. And it's some point so small that the escape velocity from its surface is greater than the speed of light. So the classical escape velocity is given by this equation here. And you can see that if we substitute the escape velocity for c, that we can rearrange and find some radius associated with this. For a given mass, what is the radius at which light cannot escape? And we call this a Schwarzschild radius, and denote it Rs. So this will show up in a lot of equations. To give you an idea of it, for the sun, the Schwarzschild radius is about 3 kilometers. For the Earth, it's about 9 millimeters. So it's very small. So the question is, what mass would this correspond to? I didn't work it out, but somewhere between the mass of the Earth and the mass of the sun. Okay. That would be very good. Okay, so here's the heart of this talk, the Schwarzschild metric. Okay? That clock is wrong. How long has that been talking?
25 minutes.
Only 25 minutes, eh? Oh, cool.
Yeah.
I'm going really fast.
That was the same.
Sorry.
Fine, it's 3:02.
All right, well, we can enjoy either getting out of here earlier or just taking time for the remainder of the talk now that we've gotten through all the boring stuff. Okay, well, that's good. So this is the Schwarzschild metric. And it's a relationship just like our other metrics. Another metric would be like the Pythagorean theorem. That's for Euclidean space, right? So we've got this term. I'm going to substitute in. So let's become familiar with C. It says that it's 1 minus the Schwarzschild radius divided by the radius. Okay. So this comes up in your equations, and we can substitute and make it a little bit nicer to look at. So what's the behavior of this? It goes to 0 at the Schwarzschild radius, right? So if it goes to 0, you see that this is 0 and this is infinity, or something like that, and we get this weird place in space at the Schwarzschild radius in the Schwarzschild metric. Schwarzschild did a lot of good work on black holes. Okay, so I've got on this slide. You remember we derived this, right? If we had done it with the radius, if we hadn't said it was just a unit sphere, we would have derived the next equation. And if we had done it in Minkowski space-time, where we have space and time, we would have gotten it to be this. But I don't know what the change of coordinates would look like in that case, so we wouldn't have done it. But you can see that these two things look very similar. It's something to do with spherical coordinates in a Minkowski-like space. Except that it's not Minkowski space because we've got these factors. And this is like time, and that's radius. So we've got...
Missing the minus signs.
I am missing the minus signs. Imagine there are minus signs there. Thank you. Yeah. The minus signs, they're important in this case. But it's not qualitatively important. And we're just going to look at it qualitatively right now. What this means is that you've got some sort of scaling of your time and how time flows, and it's dependent on the radius, because like this thing, you remember what this was, right? It goes to 0 at the Schwarzschild radius, okay? So it turns out your flow of time goes to 0 at the Schwarzschild radius, and the radial distance element becomes infinite. So you get this strange place in space, and this is like the event horizon. Which is to say that, like, if you've got something falling in, okay, I'll use my black hole. So you've got this as the radius, it's got one Schwarzschild radius for whatever mass. As you fall in towards it, there's this place where your time slows down and your radial distance gets really big, and it turns out you never cross the event horizon relative to a distant observer. So a distant observer would be like us calculating it. So I think I got the minus signs on this rather intimidating looking slide. Okay, so you remember we did the Christoffel symbols for the unit sphere? We had 8 of them. Here we have 64 of them. I've shown 16 of them in this matrix. These are all for the radial components. Okay, see there's a little art there. And luckily for us, most of them are 0. It turns out that there are only 13 out of the 64 that are not 0. And when we plug it into the geodesic equation, we get this thing, which is terrible to look at, so let's reduce it with the size. Now we've got more space on our slide. Well, not in the sense that we have more space in the GR sense. So this is the geodesic equation for the radial component of the geodesic equation. So it's parameterized in tx or tr theta in phi, right? Spherical coordinates, yeah. So this is the radial part, and that's what we care about. And it makes sense if we're talking about an infalling particle, yeah. So it doesn't have any. Yeah, here we say it. It doesn't have any phi component or theta component. So we're just going straight into the black hole. So if we let these be fixed, then the first derivative is 0, and we can get rid of this term and this term, and we just get this, right?
What is the dot with respect to?
Oh, the dot is with respect to s, which is kind of confusing. So yes, that's an excellent point. It's with respect to a distant observer. And s, we write it out. Remember, we had in the beginning of our metric, we had this is equal to whatever our metric is. Well, this can also be written as d. I think this is a little more enlightening way to look at it. And since c is 1, these things are kind of interchangeable. But this is the proper time. It's the time of the distant observer.
Of the distant observer.
Of the distant observer. I believe that's the case.
Proper time is normally the time associated with the moving observer.
I'm sorry, yes, you're right. Yes, you're absolutely right. Okay. So yes, it's the time. Yeah, it's the time of the moving observer. Okay. So what this means, we can calculate the. We've got this differential equation, right? Second order differential equation, and let's take it to the next slide. We've got it here. We're going to ask if it has any predictive power. Yeah. So let's try to model it for Earth. You can think of the Earth by Gauss's law as being a bunch of mass at the center of the Earth, right? It should be the same in classical gravity. So in general relativity, we would expect this to be the same as saying that the Earth is a Schwarzschild black hole at the center of the Earth, and we are at some distance from it of the radius of the Earth. So this would look like a Schwarzschild black hole with the mass like, or a Schwarzschild radius of whatever I said here, 8.9 millimeters. And we're at some distance from it of 6 million kilometers or so. This means our c term is very small. Right? It's roughly 1. I'm sorry, it's not very small, but it's the difference here caused by the GR effects. This is where you see the GR effects. So for a stationary object, let's start it out with r dot is equal to 0. So that's like right here. This thing represents our object. Yeah, it has no phi component, no theta component, no r component. It's just moving in time. So let's set this equal to 0, and we can get rid of this term. Okay, so now we have this. What does this look like? The beautiful thing is that this looks just like Newtonian gravity, and it turns out that if you reduce the geodesic equation for this special case, you just get Newtonian gravity back. Right? It's very nice, and this is.
Well, you said r dot equals 0 and you get that equation.
Yeah, here's r dot.
You said it.
This term
So that's not a stationary object.
Why not?
You said for stationary object r dot equals 0 and another r dots in that equation. So I'm just confused what that equation.
Our initial r dot.
Oh, okay.
Yes, so our initial. So this
If
would
you're
be like.
holding something stationary, then that's r dot equals
This
0.
would be true. This would be true at an instant before it starts accelerating. At the instant where it's accelerating. Let me. All right.
That's what you're talking about.
Yeah. More specifically, let's say that our r dot is very small. So this will allow us to be in a range like where it's stationary or once it's just started accelerating. We understand that r dot is the radial velocity, right? Okay. Good. So at the instant where it looks like this, then our r dot will be very small and it reduces to something like this. I mean, we're already approximating it. We understand that this isn't actually quite 1. It just looks very, very similar. But it turns out that, what do I have on the next slide? Okay, wait, we don't want to get to that. So these are little effects, right? I'll speak for a moment about this. These little effects are why we never really cared about it for 2 centuries after Newton did his thing, right? We worked with Newton gravity, and it worked, and we were able to make predictions with it. We were able to discover Neptune with it, like Nick talked about, and it works very well. But it turns out that there are tiny little corrections that need to be made. So here I'm approximating it to say it's the same, but we understand it's just an approximation, and that's all Newton gravity really is. It's just an approximation of the real system. General relativity proves to be a much better approximation. Is it a perfect approximation? Perhaps not, but it works really well. And so you can see that, I'll get back to this slide. This is a really complicated equation. This is what tells you what your acceleration due to gravity looks like. You can see it's dependent on all sorts of things. What your time delta looks like. We approximated that to be 1. We approximated it to be like a distant observer is like tau, right? And so we said that that's about 1, that's about 0, and that these are 0. But we understand that this wouldn't always be the case, and it would sometimes give us something very foreign to us, and these things can look very strange. I mean, they'll usually look like orbits, but there will be weird effects, like precession. We'll get to that in a minute. All right, so we see that, and that it works. It's similar to Newtonian gravity. Did anyone catch where I cheated in here? No, you can't see it. I cheated a little bit with units because we're in natural units, incidentally. It turns out that you've got to play around with it to get the natural units to work. You can't see it in here. Anyhow, but it does work. That's the point. So now we're going to talk about an interesting question, which is what do black holes look like? So this is like some old science fiction rendering of one, and it's always intrigued artists and science fiction writers, black holes. They're very interesting as a plot point or otherwise. But what do they look like? We understand that they might be more complicated than just a ball, okay? We think classically they're just black spheres, yeah? And they don't emit any light. Well, for one thing, they've got accretion disks. An accretion disk is just infalling matter that gets heated up very hot due to tidal forces and otherwise. And it's, falling in and it's spiraling in, moving very rapidly around the black hole in about a disk. And you can see that they've done that here. And we've always known that this would sort of be the case. Saturn's kind of got an accretion disk. That's what the rings are. They look like Saturn's rings, except it's much hotter. And it glows very brightly. So we might just expect it to look like, okay, so now we know the structure of what it looks like. It's just a ball with a disk around it. It looks like Saturn. But remember that our space is curved and light behaves in interesting ways. So we have to use something called ray tracing to figure out how it actually looks. And ray tracing, okay, so we're going to ask the question, why do you see what you see? If I look off in this direction, I see some shapes, yeah? I see the doors, and I see the wall. And why is this? When I look at the wall, I see light that's coming from the wall, reflected mostly, and going into my eye. It's the same for light emitted, yeah? We don't care. But in that direction, I see the wall, and in that direction, I see the door. But it turns out light is being emitted, we'll use this, okay? Light is being emitted from a surface in a bunch of directions, and only some of those rays happen to hit my eye, yeah? So if we want to simulate what we see, and we want to propagate a bunch of rays of light through space, just spoiler, did I write that here? That's what we want to do. It's not feasible to do that for all these rays. But it turns out we can make this problem a lot easier. We can say that there's an exact symmetry between the rays that happen to hit my eyes and the rays that, if I were to emit a bunch of rays from my eyes and trace them and see where they ended up, these paths would look just the same. All right. So what else do I have to say here? Yeah, that's everything. So I did some simulations. I used the geodesic equations that I calculated out of the Schwarzschild metric, which, if you remember, it's not that hard. You just find the Kristallus symbols and plug them into the equation. You get a bunch of difficult to solve differential equations. I didn't solve those differential equations. I approximated them using iteration. And so here you can see is like an orbit. This is a particle I got to go around, and it's kind of just moving. We're only propagating it forward in the straight line, but it's got this term that says that at each point it's got a little second derivative, of it at each point, and this is given by the geodesic equation. That's why we care about them. So it gives the same one, but I've propagated it around a bunch of times. And this is interesting because classically, whenever you throw something in orbit, right, it's going to come back to where it started. This is, conservation. And everything turns out to just go in an ellipse, yeah? But here we don't see that happening. And this turns out not to be a mistake on my part, but the correct thing to see. And it's because there are units here. This is starting out at 10 Schwarzschild radii. That's where we started at the particle. So we expect our GR of x to be big. C is not 1. It's something different than 1. And so we expect these effects. And it turns out that we've seen these effects. Mercury's orbit has this little precession, and we can never explain quite why it does this, where it doesn't always come back to where it started in the orbit. We can never explain why this was the case. But anyhow, it
Did
turned.
you use the Euler method?
This is the Euler method. Yeah. I did this in Python, and I could show my code, but I don't want to do that right now. So what I was going to say is that it turns out that if you do this far enough away, you will get it to come back to where it started. At least it looks like it pretty much does. In reality, it's not exactly the same place. But it will pretty much do it. I tried it at 1,000 Schwarzschild radii, and it made a nice ellipse. So the precession's only because it's so close. So this is the path of one particle, right? Now, this doesn't tell us much about what the black hole looks like. Well, we'd said that in ray tracing, what we want to do is follow the path of one particle. So let's think about a camera. If I were to take a picture of a black hole, it would be composed of a bunch of pixels. And each pixel corresponds to an angle at which light is entering the camera. So what I would want to do this the ray tracing way is send out a bunch of rays of light, one corresponding to each pixel at a different angle, and I get like a field of view that way. So if I did that and I traced a lot of rays, I traced one in this direction, one in this direction, one in this direction, and I would do this like in Python with my simulation, and I'd have in the routine a thing that says, if I find myself in the black hole, say I'm in the black hole, or if I hit the accretion disk, say the light in this direction is really bright. So if you do this, it turns out you get gravitational lensing in the movie Interstellar. By show of hands, how many of you have seen the movie Interstellar? Okay. Not a lot of you. I'm surprised. I was hoping there'd be more. Interstellar, it's great, and the coolest thing about it is that it generated this paper, besides the score, which is great. There's this paper that came out of it, Gravitational Lensing by Spinning Black Holes, and I've got it in my references. The guy you might know is Kip Thorne. Worked on it, and they did some interesting stuff, and they made this simulation, right? And they did it by ray tracing, and what do I have next? Oh yeah, but they didn't do it with the Schwarzschild black hole. It turns out that they did it with a more complicated black hole, the Kerr black hole. So these are the 4 solutions I showed on that page of solutions to the Einstein field equations, okay? Schwarzschild is the simplest. This means no angular momentum and no charge. If you have charge, you get the Reisner-Nordstrom metric. That is what explains how space curves. If you don't have charge but you have spin, it's Kerr, and if you have both, it's Kerr-Newman. So they did it with Kerr. I don't think you see anything really interesting if you're charged, so that's why they didn't do this one. But the spin gives you something interesting. You see how this isn't really symmetrical? This is spinning very rapidly this way, this isn't symmetrical because of some interesting things in the very complicated Kerr metric and how light behaves in the Kerr metric. There's this really complicated effect I don't understand at all called frame dragging, which is when like a spinning body will kind of drag space around it and it will curl. And I'm not going to say anything about that except that it exists and it's complicated. But I think you're seeing things like that, and that's why you see this very interesting looking horizon. Now, this is another picture, a slightly less stylized picture, but here you see the redshift. So you might ask yourself, what's the color of this light I'm actually seeing? Well, it would probably be more to ultraviolet, I think, because it's very hot. but here you see the receding side is redshifted because the accretion disk is moving so rapidly, and this side is blue shifted. Now let me go back to this picture. So we didn't really explain why it looks this way, but can you kind of imagine why it looks this way? Because what is it we're trying to do? I'm going to use the ball now. So you've got this, right? And imagine you've got some plane of an accretion disk around it. Okay, if you're looking at it about like this, where it's at an angle to you, you imagine that you would see light going in, and we remember there's a symmetry here. Light going into the black hole will be lensed around it, and you will in fact see the back side of the accretion disk, which is over here. You will see the image of it on top of the black hole, which is really cool. I don't know if that's how obvious that is that that's what's going on, but it provides this really interesting picture. But it turns out ray tracing gets more complicated when your things are moving at non-negligible speeds, we'll say. So it's very complicated to do what they did. But generally, that's the principle, is that they calculate the geodesic equation and they propagate light around the black hole that way. Let's see, what else do I have on here? So, yes, you've got your interesting redshift and your interesting asymmetry. And I think that's all I really wanted to say. I got through this a lot more quickly than I expected to. But that's good. I'm still under my time limit.
That's 45.
Yeah, no, it's ideal. So we figured out that you can calculate your geodesics. We showed an example how to get your metric, or maybe sometimes, I don't know how clear I made it, that what they do in the Schwarzschild and the Einstein field equations to get the solutions is they set up the, oh no, I didn't say this, here I've got one more thing to say about this. You set up a stress energy tensor distribution. So how is your matter distributed in the universe? And you try to figure out what corresponding metric would satisfy the field equations at all the points, right? So the Schwarzschild solution is where you're in a vacuum, and there's zero stress or energy or momentum everywhere, except for a delta function at the origin, right? That's where all of your energy is concentrated, and all the mass. And this is like a singularity, but I know you don't want me to say anything about those, because they don't exist. There are no singularities. We don't think. Maybe?
I wouldn't say that.
Yeah, okay, well, you wouldn't say anything about it, would you?
I mean, in the Einstein solution, you put all the mass at the center, is what you do.
Okay, yeah, it's representing a singularity.
You don't have to worry about, complications like quantum mechanics.
The Schwarzschild black hole is an eternal black hole. There's no way that it could get that way, but if it were that way, it would, barring quantum effects, stay that way, and it would look like that. Yeah? Is that fair? So the point is that you've got a mass energy distribution. I kept saying stress, I meant mass. A mass energy distribution, and that has an associated metric. So the point here is that you've got your metric, and that'll give you your crystal symbols, and that'll give you geodesics. You can use your geodesics to figure out how things move, such as light. You can use that to make very interesting simulations. So yeah. Yes. Oh, this is where I was going to say that. In Interstellar, it's great. You should all see this movie. Yeah. All right. I think that's all I've got. My acknowledgements. A bunch of good books. A lot of good lectures online. There's a series of lectures by Susskind on YouTube on general relativity that are really, really good. I also like to thank Thomas here and Reed, who is not here today, because they've been explaining this stuff to me all semester. So yeah, I definitely wouldn't understand it at all without the help of those guys, and with a lot of great books. So now you understand general relativity. All right. Yes.
You go back to the first black hole picture,
This one or the
yeah,
previous
that
one?
That. So there's only one disk around.
Yes. Yes.
And we're just the top and bottom part we're just seeing the other side of the disk
Yeah.
from the bottom and from above.
You know, I've got here. Where is this? Oh no. Oh yeah, here it is. Okay, I've got this. If you haven't seen Interstellar, this shouldn't contain any spoilers. But it's really cool. Okay. This is when they approach the black hole. That's the spoiler. But there's Matthew McConaughey. Look, that's the thing. That's how it looks. Isn't that awesome? Let's watch it a little longer. What is it, Charlie? What is it? Yeah. Sorry, that's really loud, but it's great. Yeah. So you get this really cool lensing effect, but to look at that and not know anything about it, it's like, okay, that's an interesting shape. They're going around. But to look at that and realize that it's flat and it just appears that way because of the gravity, it's so incredible. I don't know. And another thing I should say is that a big plot point in that movie is the time dilation. And I didn't explain time dilation at all, but time dilation is expressed by the geodesic equation for time. How does the particle's time look along its path through space-time? Because you usually think about a particle traveling through just space, and the time is what parameterizes it. But it's a little confusing when you're in space-time, because the time is also parameterized. But it turns out when you approach a black hole, your time, relative to a distant observer, really slows down. So that's why and you can look at that, you can look at the geodesic equation for the time, and that will tell you the time dilation. And that's what they're experiencing here, time dilation. It's a big, really good part of the movie.
Yeah, other questions?
Yeah, any other questions? Nick?
So you said there aren't very many effects, but what are the effects of charge solution?
Oh, shouldn't have asked me that. Yeah, I don't know. I've only given them a cursory look, really. I don't have any idea. I know that the equations are complicated. You never know with these things. I don't think anyone's ever tried to ray trace a charged black hole to my knowledge, so I don't know how it would appear. I would guess, I believe, at least the Reisner-Nordstrom metric, which is just charged black hole with no spin, that one I think is spherically symmetric. I can't imagine why it wouldn't be. So I think you would just see what you would see with the Schwarzschild black hole.
It seems odd to me, just in mind you guys that like you wouldn't see any difference in gravity because
No, I'm sorry.
like Einstein's field equations don't care about whether things are charged or not. I thought. Right? Or like, do you need like aerodynamics?
Would you? Oh, that's a good question. I think that because I know, here's what I do know. I know that the metric for the Reisner-Nordstrom metric is different than the Schwarzschild metric, and I know that you figure out what the gravity looks like there based on the geodesic equations you get out of the metric. So my guess would be that yes, the gravity would be slightly different, just because you're driving them from different things. Yeah. Does that answer your question, Nick?
I mean, the deal with that is that, charge makes a difference, but it's not that it's harder to calculate. I mean, the thing with charge is that black holes throw off charge very rapidly. I mean, they neutralize very rapidly.
Oh, is that right?
So you simply don't find charged black holes in space.
That was my question, because
But
if
you do
you
find
overcome the charge in order to create a black hole, like it's not one of the things that overcome is that like all of your electrons only be in the same place, and then when you get past that, like it crashes into protons, and so how would you have a black hole with charge if that's occurring?
That's an excellent.
Well, there's a limit to the charge you can have. I mean, if you put enough charge into a black hole, it's going to like explode. From electrostatic repulsion. But you can theoretically put a big excess charge into a black hole, and the electrostatic repulsion will be overcome by gravity. As long as your charge is not too big. But regardless, big charge, little charge, it simply neutralizes itself very rapidly. Just very rapidly. Whereas the spin down can take billions of years.
Yeah.
So I mean,
What is the way that it neutralizes itself?
Oh, if it's positive, it'll suck in electrons from interstellar matter around it, and then throw off the protons.
Okay. Oh, that makes
You know,
sense.
it'll break apart
Okay.
the atoms and suck in the electrons and throw the positive charge off.
Okay. Oh, right, that makes
You know,
sense. Yeah.
or
Yeah.
vice
that-
versa. If
yeah,
it has the
absolutely.
other charge.
Certainly.
It will break apart the atoms around it
Sure.
in the interstellar gas.
Yeah.
And it's simply a very rapid process.
Yeah. Okay. Yeah. So, Nick. Yeah. But do you agree that the gravity would be different? Is that what you asked, Nick?
Yeah, it makes a difference. Yeah, absolutely. The geodesics are different.
Yeah.
If it's charged, yeah. So you can do, these.
The charge? It's in the stress energy tensor. Yeah.
You add an electromagnetic term in the stress
And
energy.
energy momentum tensor for the electromagnetic field.
Yeah. Yeah. Exactly. Yeah. Yeah. Exactly. It would be in the stress energy tensor. What was your question, Sarah? Oh, okay. All right. Yeah. All right. Yeah. So, anyone else have any questions? All right. Is there anything I missed in here? Did you have any objections? Yeah.
No.
No. Okay.
Let's thank the speaker again. There's plenty of pie.
Yes.
Very nice talk.
Yes. Please come and have more pie. And I'm just gonna play Interstellar a little bit more.
Yeah, especially if you have like Matt Damon.
Yeah. You want Matt Damon? I got Matt Damon.
It's not noticed. The Martian?
No, not the Martian,
Oh,
Interstellar.
oh, he's in Interstellar.
Yeah, no, they found his planet.
Oh, that's right.
They
He
found
was,
his
I
planet.
forgot that. He was, oh, so he's
He's
used
living
to
there.
this world, right? Yeah, he has experience.